Hello students, welcome back to Algebra 1. So today we're going to have a little bit of an unusual lesson because we're going to be mostly depending on our technology today. So these are the three different functions that we've talked about in this class. We've talked a lot about linear functions in Algebra 1a, y equals mx plus b, and these are the functions that grow in a straight line, or they decrease in a straight line. And we spent several weeks talking about exponential functions, where we start with a fixed amount and then we increase by multiplying. And for the past several weeks, we've been talking about quadratic functions. So in real-world situations, we will get some data and we will choose how we are going to model this data. So if something is growing at a steady rate, it's constantly going up like this, or down in the opposite direction, we would want to use a linear model. For example, this might be something where somebody is earning money at a steady rate or saving money at a steady rate. Where something else, like if you had some money and you invested it and you were growing by a percentage every year, that would start to grow sharply, so we might want to use an exponential growth. For a quadratic function is going to start growing slow and then grow faster and faster and faster. But unlike an exponential function, if you go in the reverse direction, it has the same effect. So again, an exponential function can grow in a curve like this, but on the other side of it, it's going to keep on getting flatter and flatter. So we are going to use technology today to answer the question, which of these would be the most appropriate? So we're going to use graphs to identify functions, plot the points and tell whether the points appear to represent a linear, exponential, or quadratic function. I'm going to add on to this, then write the equation of the function. Now, for Algebra 1 students that can't use technology, this can be a daunting task. However, we are going to use a technique called regression that's going to make this very, very easy for us. So I'm going to shrink this to the side, and now here I am in Desmos. And in order to plot points on Desmos, I'm going to push the plus button here. I'm going to create a table. So I'm just going to type this in: 4, 4, 2, 0, 0, 0, 1, negative 1/2, negative 2, 4. So I'm looking at this here, and obviously it doesn't go in a straight line, and it does pop back up. So immediately I think that this is going to be a quadratic equation. So going back up to my chart here, I see that my quadratic function is y equals ax squared plus bx plus c. So if I want to find the equation, I can very easily have my technology figure this out for me. So if I type in this equation, y equals ax squared plus bx plus c, I don't get anything, because what I need it to do is to tell it to specifically look at this chart up here. So first of all, this is meant for working with scatter plots where it's not going to always hit every single dot. So in order for me to tell that, I'm going to erase the equals, and I'm going to put the approximately symbol in there. Now on my keyboard, that button is directly to the left of the 1 key, so I push shift and then that button to get that. But if you're using an iPad or some other touchscreen device, I can go here to say show keypad, and then we'll look for it here. I don't see it. Let's go to functions. Nope. Oh, that's right, it's in here. So I went to the letter keyboard, and then there it is right there. Okay, so you notice still nothing's shown up. That's because this is x1 and y1. So I'm just going to go here and say y1, x1, x1. And there it is. There's my parabola. You see that it connects all of the dots perfectly. So in order for me to write the equation, I've got ax squared, bx, and c. Well, it's telling me that this is what a, b, and c are. So I'm going to type this in. Y is equal to 0.5 x squared minus 1 x, and then this one right here, plus 7.546 times 10 to the negative 17th power. Now that's a very small number, but you notice that if I just erase this right here, it looks like it's directly on top of it. That's pretty close. But this would technically be the right answer, 7.546 times 10 to the negative 17th power. Okay, so let's go and check on the other two examples. So I'm going to go ahead and just delete these. We'll start over. I'm going to create a table. 0, 1, 2, 4, 4, 7, negative 2, negative 2, negative 4, and negative 5. Okay, so this one appears to be linear. It's going in a straight line here. So I would use y equals mx plus b. But again, not equals, approximately, y1 equals mx1 plus b. And here it tells me that m is 1.5 and b is 1. So my equation is y equals 1.5x plus 1. Okay, let's do one more. So again, let's create a table. 0, 2, 2, 8, 1, 4, negative 1, positive 1, negative 2, 1/2. Okay, so now here I'm seeing a pretty clear exponential. So that means I want to use y equals a times b to the x power. But again, not equals, is similar to, is approximately y1 abx1, and there it is. A is 2 and b is 2 in this one, so that means I would get y equals 2 times 2 to the x power. There's my equation right there.